Hi, today's our first class on regression, and we're going to begin that topic right now. So with regression, we are asking about the relationship between two quantitative variables. For example, the question we'll be asking in this lecture is whether or not there's an association between smoking cigarettes and lung cancer. So up to this point, the work we have done in class with data sets have been just with a single variable. So for example, the cancer data set, which is on Campus Cruiser and which is the data set that's in your notes, it's the data set that's used in the quantitative data lab. That data has in it smoking prevalence by state from 1960, and it also has in it deaths due to cancer per 100,000 of the population for different states. So this particular diagram is for the lung cancer data. So if we looked just at smoking prevalence alone, the histogram is like this. And we also have some descriptive statistics here. So on average, there were about 2,500 cigarettes smoked per capita by state in 1960. These numbers are in hundreds per capita. And so, this varied by states. If we look at the shape of this, it would be almost right skewed, and because it looks like there would be, a sort of a tail feature over here. But you can see that it varied. One state, this state in particular, had more smoking than other states. This is a picture just of the incidence of lung cancer in the 43 states in 1960. So it does have somewhat of a bell shape to it, but it looks like there might be a slight left skew in this case. So these are the summaries of just those variables, not the variables considered together. Here's box plots of the same variables. This is the number of cigarettes smoked in hundreds per capita by state from that data set. And you can see here it does seem to have a bit of a right skew, and that there are some unusual values in that data set. This is a box plot of the number of deaths from lung cancer from the 43 states that we have data from, and there does seem to be a bit of a left skew. This distance is much longer than the distance on the other side. So this is what we see if we consider the variables separately. But what can we do, how can we see the association between these two variables? To see the association between the two variables, you can make a scatter plot. And in this scatter plot, the number of cigarettes would be the X, the independent variable, and then the number of deaths due to cancer is the Y variable. So that's the dependent variable. So if I did this for the lung cancer data, so again, the x-axis is the number of cigarettes smoked, the y-axis is the number of deaths per 100,000 from lung cancer. So if you look at the data now, does there seem to be some kind of trend in the data? So that's the question that we're asking here. So in general, a positive association occurs when large x's are associated with large y values. So in each of these cases, as x increases, y is also increasing. And in this last case here, this is an example of perfect linear association. These points are actually collinear. And as you go backwards here, these are a little bit less collinear. And these, while they have a linear trend, there's a little more scatter than you can see in the other cases. Now these examples are examples of negative association. Negative association is x increases, y is decreasing. And in the first case, there's certainly seems to be a trend, but there's a lot of scatter here. There's certainly less scatter here. And in this last case, this is perfect negative linear association. So to measure the strength of an association, we have a statistic that we're going to use. It's called the correlation. It's indicated by the small letter r. And this statistic is going to give us a measure of the strength and the direction of the linear association between two variables. Just so you know, R represents a sample correlation coefficient, and in general, rho represents the population correlation coefficient. We, in general, will not be using this letter for correlation coefficients because we don't have population data. We will generally be working with sample data. So the correlation coefficient does have a few properties. It's always a value between -1 and +1. +1 is perfect linear positive association. -1 is negative linear association, meaning it would have a negative slope in that case. So as x increases, y is decreasing. If you change the scale for the variables, the correlation coefficient is not going to change. Similarly, if you interchange x and y, the value of r is not going to change. Other items that we're going to be computing with in this topic in regression will not have this property. This property is unique just to the correlation coefficient. R does measure the strength and direction of a linear relationship. But as you know from our first day of class and the articles that you read or you heard about when they were reported in class, the correlation, having a very high correlation, does not imply causality. Causality is a different beast altogether, and while they may be related, maybe correlation is necessary for causality, it is by no means sufficient for causality. Okay, so here you can take a look at these. You have these in your notes, and each of these would be assigned either low positive, high positive, low negative, high negative, or no correlation. So why don't you take a moment and think about, what these would be. High positive, low negative, no correlation, low positive, high negative. Make sense? So here's also, I don't think I put this on your notes, I may have added it later. There is an applet where you can play with this concept. And where do I have that? I think I have it here. So the URL is here, rossmanchance.com, applets guess correlation. So here you can generate a sample of points and guess the correlation. So that doesn't look very correlated to me. I'm going to guess 0.2. And it's even less than 0.2. So I think I want more points. And if I generate another sample, now this does seem to have a positive trend to it, but it doesn't seem so strong. So the correlation guess here, since it's positive, it's positive slope, it'll be a positive correlation. I would guess maybe 0.4, and we can check 0.5. So you could play with this a little bit and get a feel for the correlation coefficient with a scatter of points. This one's clearly also positive. I want a different sample. Let me have a negative sample they're getting. That one's negative. So this is a negative trend, very weak association here, but there's definitely seems to be some association. So I would guess maybe 0.4 again. Oh, I forgot negative. Oops, sorry. So evidently it's about negative 0.3. That's also negative. Maybe I'll try negative 0.4 in this case. Nope. and it's a little bit, an absolute value a little bit more. So hopefully you get the idea. You can try this on your own and see how you can manage with that. So those are at this site. Oops. Okay, we did this. So here's a few more patterns, and here's the correlation coefficient associated with them. Perfect, collinear points, the correlation coefficient is 1. Provided the slope is positive. Here the slope is negative, so the correlation coefficient is -1. The slope itself does not have to be -1 for the correlation coefficient to be -1, and you can see that in these cases. So in each of these cases, the correlation coefficient is -1, even though you can see by inspection that the slopes differ. The same thing for the positive side here. These correlation coefficients are all +1, even though the slope of the line is not in fact 1. Here you can see as the scatter increases, the correlation coefficient gets closer to 0. And in fact, if there's no relationship at all, the correlation coefficient is 0. These are some interesting cases, all of which have correlation coefficient 0, even though there does seem to be a pattern or trend in the data, but these trends are not linear trends. Okay, so if you have a data, a data set, and you have two variables, you have bivariate data. One variable you're considering to be the x variable, the other variable you're considering the y variable. The x is called the explanatory variable in this topic. The y is called the response variable. So what we're going to be looking at are models that are just linear models. So if you have data like this, there's no one single line that passes through all the points because the points are not collinear. But the question is, what's the best line to use for the model? If we wanted to make a linear model for this data set, if we decided there was a linear relationship between the number of cigarettes and the number of deaths, what would be the line that best models this relationship? So what do we need for the line? We need the slope and we'll need the intercept. So turns out, and I will put the details for this on Campus Cruiser in a PDF file, you can go through a process that involves some calculus and some more advanced math than probably what you've been exposed to. But you can derive the regression coefficients of the slope and the intercept using this technique called least squares. This line is a unique line, meaning there's only one regression or best fit line, and to find that line we use a process called least squares. So least squares is a process where you find the coefficients of that line where the sum square of the errors is the smallest. So we'll make this picture later on in this session, but for now we will try to understand what does it mean, what is the regression line? The regression line is that line where the sum of square errors is a minimum. So in this particular example, it's a very simple example. There's a few data points. Here's a data point in blue. Here's a data point in blue, data point, and data point. Right? So there's 4 data points here. And for each of the data points, the regression line is shown. That's in blue. But for each of the data points, you can see that there's a difference between the y value of the data point and the y value on the regression line. This difference is called the error or the residual. So in this case, the residual is negative, because if you take y from the data point and subtract it from the y value on the line, you would have -5. And so for each of these points, these data points, you could calculate the these residuals, these errors. They're just the the data point value, subtract the y value from this line, right? So when you square the errors, what you really have, another way to think about it, or one way to think about it, is when you square the errors, you have the areas of these squares. So the regression line is that unique line where the sum of these areas would be the smallest. It's the least. Okay. So here now you have a chance to practice this. I have a small, very crude example here. Here's the line. Y is negative 5/2 x plus 4. That's this blue line. And near this blue line is nearby the 4 red points. The red points represent the data points. So what I would like you to do for this example is find the sum of the squared error. Okay? So how are you going to do that? Well, I guess I can start you off on this. What you'd want to do is identify an x value, like this point for example, x is equal to 0. Now this x value is associated with a y value on the line. That point is here, and you can always find those by substituting in the value for x. When x is equal to 0, clearly y is going to be 4. But this x value is also associated with a y value that's a data point. This data point is x equal to 0, y equal to 1, 2, 3, 4, 5. Y is equal to 5 in this case, right? So from the line we get 4, from the data value we get 5. So we can take the difference between them. Difference between them is clearly 1, and you can square it. So that's going to be the squared error for this x point. So you would do that for each of these points, and when you add them up, you would have a total sum square error. So you can pause at this point, please, and find that for these points. Okay, so hopefully you've done that little exercise. I know this doesn't line up so well, but you can see for each of the points what the squared error is. And so the total sum square error for this particular line is 9.5. 9.5 for this line and these data values. So that's not necessarily the regression line here. For the regression line, of all lines possible, that error would be the least. It would be the smallest possible. So here you could also play this and see this idea on StatCrunch. I have the the instructions you need to do. If you open StatCrunch, go to Applets and Regression by I. We can play with this for a few minutes and find the least squares line. So we could do that now. Let's see, where is that? So you have to log in, and if you log in, open up StatCrunch, and from StatCrunch, what we want to do is go to Applets, Regression by I, and then we'll generate some data. Okay, so Applets are here. Regression is in this list, and we'll do Regression by I. So we're going to randomly generate the data, and if we just do compute, it'll give us a data set, which is here. I would like to have some more data, so I'm going to make my sample size a little bit bigger, which is there. And so here's the data. It almost looks pretty cloud-like. The user regression line is this green line. Now we can move this around, and what it's doing for us automatically right here is it's computing the sum square error, which is what we just did in that crude example. So the sum square error with the current placement that I have for this line is on the order of 1900. That's taking the data value minus the y value and squaring that for each of the points. And you can see as you move this line around, the sum square error changes. And I guess the smallest value it takes on is 1165.71. Now we might be able to maneuver this in such a way that we can actually find that value, although I don't seem to be very good at it. You may have better luck than me. So I am reducing my sum square error somewhat by moving this line down, but then I maxed out on that. So you can maneuver this for a while. What you're trying to do again is minimize the error, the sum square error. And so after you've done that for a while, we can also see what the exact position of the regression line is. It's here. So if I had moved my line to that location, at that location, the sum square error is actually the least. Mine's not exactly on that spot. Okay, you could try this again. Maybe it's a little easier with more points. There's another one. The regression line's already there. If we remove that, then you can take your user line and try to put this in a location or in a position that would minimize the sum square errors. So, because there, as you know, there are infinitely many lines that, that could serve as an approximation, but there's only one line that has this property that the sum square errors is the least. So that one particular line is this one, this regression line. And that line, for this particular data set, the slope is 0.83 and the intercept's approximately 1.7. Okay, so that was this exercise. So here, I think your notes might be slightly in a different order. I did switch these around a few minutes ago. So you do have this this note, but it might be a page or so later in your set. When you use the regression process to estimate the slope and the intercept, you can interpret these in the usual way, sort of. This beta hat 0, this is the estimated regression intercept, and beta hat 1, this is the estimated regression slope. These are estimates of population regression coefficients, which we do not have access to. We are estimating those based on our sample, and there is error involved. And however, when we think about these values, we can interpret them as in the following ways. The y-intercept is interpreted as what we would expect the y value to be when x is equal to 0. Now, we do need to be a little bit cautious about this, because that value is not necessarily going to be meaningful. Sometimes it will be completely nonsense, because either x equal to 0 is outside of the range of data that we have, so that it's not valid. Our model wouldn't necessarily extend back to x equal to 0. It could also be not valid because the value we get is nonsensical in the context of our application. So the y-intercept, we do need to use that, think about it a little bit cautiously. The slope represents, what is a slope? A slope is the change in the y over the change in x, delta y over delta x. Now, when you have a number, that ratio is going to be the number, whatever that number is, over 1. So that slope will represent, if it's positive, it will represent the increase in y that we would expect for a 1 unit increase in x. If the number is negative, if the slope is negative, it's the amount of decrease we would expect in y for a 1 unit increase in x. So we'll practice this now on the calculator. If you've never used your calculator for regression before, then you do need to do something the first time. So let me open up my calculator. Okay, so if you have your calculator on, then just mention, if you want to use this for regression, you have to turn the diagnostics on. So if the calculator's on, if you go to the catalog, you can see catalog here at second 0. So if you go to the catalog and you scroll down to, I'm in alpha mode, so I clicked on the X inverse key so I can get to D. You scroll down to diagnostic on. It's this command. So if you enter that command, then when we use the regression subroutine that's sitting, that's hard-coded in your calculator, you'll get the regression coefficients as well as the correlation coefficient. Okay, so here's our first example. And in this example, we have study time and GPA. So we have two quantitative variables. This study time is in hours per week, and this is the student GPA. So I have all of this, I have the instructions here, sort of, for you to do this exercise. So to enter the data, we'll go to Stat and Edit. Now the assumption here, well, when you have a data set like this, you have to think about what's the independent variable, what's the dependent variable. So in this particular case, a student would have direct control over their study time. So this would serve as the independent variable, and the dependent variable would be the GPA. And if you think about it a few minutes, that should make some sense to you. So I'm going to put the study time in list 1. That'll be the X values. And then the Y values are the GPA. Okay, so I have them in. It's anytime you add data into your calculator, it's always a good idea to check to make sure that you didn't, make a mistake keying something in. Because as we'll see next class, when you compute the regression coefficients, the calculator will do this for us automatically. Excel will, and all these programs will do that automatically. The formulas are coded inside, but the reality is they all depend on summation, so every data point is used in the calculation for the slope and the intercept and the correlation coefficient. So if you've made an error entering any of the data, then all of those calculations will be wrong. They'll be off. Okay, so if I quit here, then what do we need to do? So we entered the data in lists 1 and 2. Then step 2 is we're going to go to Stat, and then over to Calc, and then we're going to choose 4, linear regression. So if we scroll down to 4 and choose linear regression, then if you press enter at this point, the default is the X variable is in list 1, the Y variable is in list 2. I don't like to rely on the defaults. I like to identify exactly where my X points are. My X points are in list 1, so I put list 1 here. To get list 1, it's just second 1. Then above the 7's the comma key, and second 2 is list 2, so that's the Y value. So this is X point, comma, Y point. So when we have the calculator do this calculation for us, I have the screenshot here for you, and lots of stuff comes up. So I'll go back to the screen. So what do we have? We have the regression equation. It's a line, ax plus b, which is the same as mx plus b. So a is the slope, b is the intercept. We have something called r squared, which we'll talk about next class, but we do have something called r, which we already spoke about. This is the correlation coefficient. So, well, we could start with that first. What's the correlation coefficient? In this case, it's about 0.81, and so that would indicate a strong, positive, linear association between these two variables. And in fact, if you look at, I did plot this data in a calculator, and you can see the points are pretty close. They do seem to have a linear trend, and they do hover pretty closely near the regression line. So again, the correlation coefficient of approximately 0.81 would indicate a strong, positive linear relationship. Okay, we also need to interpret the regression coefficients. Now there are two regression coefficients. There's a slope and an intercept. The intercept here is 2.6, right? Approximately 2.6. So what does that mean? Well, I think I have this all ready for you in your notes. So the intercept, if the x value was 0, in other words, if the study time were 0, we would expect the GPA to be about, this value, 2.63. Now, you have to think about, does that make any sense? Well, that's not going to make any sense for a variety of reasons. A, it makes no sense in this context. If there's no study time, you wouldn't expect the GPA to be this high, so it doesn't make sense in the context of the problem. But the other issue is the smallest x value is 5. These values are all bounded away from 0. So x equal to 0 is not in the range of our data, so we have no reason to believe that this linear model would hold up for that value of x. So that value, the intercept is not reasonable and is not reliable nor meaningful in this particular case. The slope here is what? The slope is about 0.04. Yeah, or 0.044. So what does that mean? So the slope is the change in y over the change in x. So the change in y is the change in GPA, and the slope is positive, so we would expect a 0.044 increase in GPA, increase because the slope is positive, a 0.044 increase in GPA approximately for each additional 1 unit increase in x. The 1 unit increase in x represents 1 additional hour of study time per week. So I do have that written here for you. What's the predicted GPA for someone who studies 5 hours per week, 25 hours per week? Okay, well, if you look at this, 5 hours per week is in the range of data, 25 hours a week is in the range of data. There does seem to be a linear relationship here. The linear relationship seems to be fairly strong. So we can use the regression line for interpolating and approximating. So if you substitute in x equal to 5, you would get approximately 2.8. So for someone who studies 5 hours a week, you would expect the GPA to be about 2.8. For someone who studies 25 hours a week, again, you can substitute in using your calculator. You would get approximately 3.7 is the GPA. Okay, so now you have an example in your notes. There's lots of, I gave you quite a bit of, quite a few screenshots here. But so what is this? This is a question about baseball scoring using batting average. So here's a bunch of different, teams. I recognize New York Yankees. I guess this is Boston, Cleveland, and some other teams. I'm not such a baseball aficionado. But there's a bunch of teams, and so this was the batting average from some particular year, batting average overall for the team, and the team scoring. The team scoring is the team's mean number of runs scored per game. So it's the mean number of runs scored per game. So the question is, can you use the predict the scoring, using the batting average as the explanatory variable? So can you predict the baseball scoring using just the batting average? So you can put this data in your calculator. The independent or explanatory variable is the batting average. The dependent or response variable in this case is the team scoring. And if you do that, and you run the linear regression, you should get these results. So you might want to pause the video now and put this data into your calculator and confirm that you would get this slope, this intercept, and this correlation coefficient. And in fact, the data does look like this, which which, there's definitely some scatter here, but does seem to have a positive trend, and does seem to have somewhat of a linear relationship. Okay, so why don't you do that and pause this, and then we'll continue. Okay, so the first question is here, what's the regression equation? Well, for the regression equation, I guess I didn't really write that here, but the slope is 26.4, the intercept is negative 2.3, so the regression equation would be y equal to 26.4x minus 2.3. That's the estimated regression equation. Our next job is to interpret the regression coefficients. That's going to be something that you need, you're going to need to do this in your exam. This is something that you're supposed to do when you do the homework. You do need to be able to interpret the regression coefficients. So based on, the discussion from the last example, you may come up with these interpretations. For the y-intercept, we would expect its team scoring to be approximately negative 2.3 when the team batting average is 0. Clearly that's not meaningful for this application. For the slope is this number, right? 26.4. Well, 26.4 represents the change in y, the change in team scoring, over the change in x, the change in batting average. 26.4 is itself 26.4 over 1. So the change in the team scoring is 26.4. The change in the batting average would be 1. So we would expect an increase in team scoring of about 26.4 for a 1 unit increase in batting average. If you look at these batting averages, that would just appear to be miraculous because there doesn't seem to be such a large increase in batting average if you look at these teams. So that is how you would interpret the slope, but it doesn't seem to be terribly realistic in this application. If the team has a batting average of 0.275 next year, what's their predicted mean number of runs per game? So for this case, R is a reasonable value. It's a moderate moderate positive association between these variables. This does seem to have a linear trend, so you could use the regression equation as a predictor here, and if you do that, you would just substitute 0.275 in the linear equation, and you would get about 4.96. So the team, if the team has a batting average of 0.275, we would expect the mean number of runs to be almost 5, approximately 4.96. So this work can also be done in Excel. I have in your notes how to do that. You would put study time and GPA, into Excel. And well, we'll just do it. So I'll put this, minimize this for the moment, and let's see, do I have something here for that? So I think, you know what, I'll just open this up. It's already, I don't want any of these, but I'll just open up a new page. So okay, so here's a spreadsheet, and this will be the study time, and this column is GPA. Okay, so we'll just enter the data in the usual way. Okay, so those are the study times, and then for GPA, we need to enter. Now these are ordered pairs, so they have to be associated with. The first study time has to be associated with the first GPA. These are ordered pairs. These are study time and GPA for particular individuals, so you have to keep them associated. Okay, so like before, I'm going to check to make sure I have entered the data correctly. It's really important because if you make a keystroke error, then everything's going to be off. Okay, so it looks like it's okay. Now to do this, you just want to highlight the data, and then we're going to insert a scatter plot. So here's a scatter plot, and we just want the first one, basic scatter plot. Now once you have a scatter plot of the data, you can right click and add a trend line. So if you add the trend line, you have a bunch of choices. The only choice we're going to use is the linear. We want the linear, and we want the equation on the chart, and we'll put r squared on the chart. So when we've done that, we have this, we have this, this result. Now what I'm going to do is a few things. I'm going to get rid of the grid lines because I find them not useful. So I got rid of those. The trend line is there. I wanted, no, okay, so I guess I'll leave that. I would prefer this style. I want a solid trend line, so I played with it a little bit to get a solid trend line. This version of Excel, you know, that was an option. If you use older versions of Excel, you do get a solid line. Okay, so the other thing is this font size is way too small. So if you select that box and you know, select the Home tab, you can change the font as well as the size. So I made it a bigger size. The other thing for this chart to be a decent chart, let's see, where am I in this notes? We did that, we added the trend line, we did that, we're here. So to finish the chart, you do want to make sure that you have a title and axis labels. So in this particular, this is a newer version of Excel that I'm running here. Let's see, if I double clicked on this, and I'm going to look at quick layout. So quick layout, what are the options? There's different options. This first option, you can get a title, X and Y axis labels. You can also get this, you know, this other, what is this thing called? This is a little legend that we don't need, so I'm going to delete that. But now I have a title and X and Y axis labels, which are, anytime you do charting, it's very important to have title and X and Y axis labels so someone who's looking at your chart knows what they're looking at. So I would normally put something about the data here, but I don't actually have that information, so I'll just repeat the question. What we're asking is, and I'm not, this is doing it all in caps, I'm not so keen on that. So, and I have no choice in this at this moment. Okay, so is there a linear association? I'll just leave it at that. Now the x-axis here, this is study time, and that's in hours per week. So you'd want to put the units as well as the label, and then this axis is the GPA. Okay, so okay, so now I have a chart. Oh, I lost my trend line. I'm going to put it back in. So to get the trend line, I'm right clicking on the mouse. I'm going to add a trend line, and I want to include the equation on the chart and r squared on the chart as well. So those have appeared again. I want to get rid of those axis lines and I do want to change the size of this. So this is actually very large. I made it a size 14. I'll probably reduce it to a size 10. And I'm so unhappy with this title. And I guess I want to get rid of the bolding, and I also don't want this box around here, which I'm not sure why I have it. So I want no box. And so that's the the rudimentary chart that I have here. Now, if you have Word open, if you have a Word file open, like a project, for example, then you can make a copy of this chart. You can select the chart, do a Control-C, and then you can include your chart in your document, which is here. Okay, so that's that. So you should be able to make a regression line in Excel without too much difficulties. Okay, so that's it for now. Your homework is to review the material we discussed so that you know what's going on, because when we meet again on Friday, I'm going to do part 2 of this topic, and you do need to be familiar with part 1 of the topic for part 2 to be meaningful. So please review the material and know how to do what, the examples that we did. Make sure you're familiar with them and that you can do them. There is no homework for this on my stat lab, for a variety of reasons, none of which I'll go into at this moment. But there is homework from the syllabus, so to remind you about that, from 11.1 and 11.2. You can use your calculator to do these problems. You would be expected to know how to find the regression coefficients, find the correlation coefficients using your calculator, and interpreting all of them. And what does the correlation coefficient mean? What does the slope mean? And what does the y-intercept mean? Okay, so next time we will continue with more of this topic.